The analysis of the spliced post-tension I-girder bridge, and this is in Woodburn, Oregon. It carries Oregon 214 over I-5. A quick outline of the presentation overview. I'll be going through the project and the structural description, as well as the following presentation topics. And my plan here is to go through all these topics briefly in a PowerPoint presentation and then move right into the model and have a look at how all these topics were integrated in my model and compare some results between the alternative modeling options that I went through. So we'll be looking at a grillage model development with composite sections, time-dependent material properties, the effective properties, the construction stage analysis, including the boundary conditions, pre-stressing, both pre-tensioning and post-tensioning, the loads and load analyses, and then the combinations and envelopes. So the project description, Summit took care of the superstructure analysis and design of the highway overpass widening. McGee Engineering took care of the remaining design, including the seismic analysis and design of the substructure. Oregon State Bridge Construction is building the structure, and Knife River Precast the girders. What I did was perform the stage analysis with the high skew effects, and then also looked at the seismic response in addition to the moving loads and superimposed dead loads. The structure is a four-span continuous I-girder bridge using the BI-51, which is an Oregon section, and has a haunched pier segment. The spacing is 8 feet 3 inches, and it's about a 34.5 degree skew, with 9 KSI precast concrete and 4 KSI field concrete. Here's just a plan view of the structure. The existing structure is toward the bottom of the screen with the 5 girder widening toward the top. And a section view of the widening as well. For the model, we use composite I-girder sections with the cast-in-place deck as the second part of the composite, with just a two-part composite section. Also applied effective section properties for piers and the bent caps. The reason we did this was because the post-cracking behavior of the piers allowed them to be a little bit more flexible, and the bent caps were experiencing high degrees of compatibility torsion, which did not affect the equilibrium of the structure, however, attracted a lot of torsion with any kind of differential loading. So did some research and were able to reduce the torsional constant of these sections, allowing for more efficient reinforcement just based on the true behavior of the structure. Also looked at the time-dependent material properties modeled using CBFIP90 and modeled the time-dependent properties and took a look at what day each element was built. A brief overview of the grillage model. Hambly's bridge deck behavior does a great job of explaining this. And it allows us to model the composite sections with the deck elements acting compositely in the longitudinal direction. However, then we impose transverse weightless elements for the distribution between the girders. And the reason these are weightless is so that we get the action in the transverse direction, however, don't impose any more dead load on the structure. The time-dependent properties, we have a creepage shrinkage model and then also the modulus time-dependent. The time of constructing these elements we found was very critical to their behavior. For the modulus, it's important not to construct an element at an age less than 3 days, just to allow for the modulus to reach a reasonable strength and not get excessive deflections. The CEB-FIP90 model takes the concrete compressive strength, the relative humidity, and the notional size, which is the 2 times the area over the perimeter. For the effective section properties that I mentioned, we use the effective moment and inertia for the pier bending. And The value I got from this came from a lecture by Priestley, and for typical bridge piers, this value would reduce the gross property by anywhere from 0.3 to 0.6. We use 0.5 for this structure. With the bent caps, as I was explaining the torsion, we were able to reduce to an effective property of 0.1 the gross torsional constant. For the pre-stressing, we had pre-tensioning in each girder segment and also post-tensioning. And to put that in MIDAS, we defined the strand, defined the PT layout, and then defined the load. On the construction stage analysis, the stages 1 through 10, we constructed the girders, stressed them in the bed, then erected in the field and casted the splices and the bed caps. Post-tension, poured the deck, allowed the deck to cure, superimposed the dead loads, and then aged to 30 years. Then, of course, there were the moving load analysis and seismic load analysis on top of that. The boundaries I used are shown in the fourth column here. I used spring supports for a casting bed, and then compression-only springs once I took them to the field to simulate shoring towers. The alternative option here is to use vertical restraints, run the model, and analyze whether or not the restraint was restraining the girder in a downward direction, and then rerunning the model and releasing any of those that were restraining the girder downward. Shoring towers won't ever hold a girder to the ground. It can only keep it from deflecting. And then once we get into the deck curing, it's just the pin to fix connection of the piers. The loads I modeled were dead, thermal, live, and seismic, as well as wind and the braking that came along with the live loads, although for the superstructure that came out to be fairly insignificant. The two images here I have are the Oregon permit truck, as well as the response spectrum function from the seismic analysis. A quick overview of the moving load analysis. The live load with the HL93 had a maximum of 5 lanes with a maximum of 3 lanes loaded at any time, and that included an impact factor, multiple presence factor, and a lane load. The permit load, we restrained that to only the center 3 lanes with a maximum of 1 at a time, and that was because in a permit situation it would likely be 1 at a time in the center of the bridge. For the load combinations, I did load combinations for both strength and service to check service stresses throughout the construction stages, and then also check ultimate strength. I set all these load combinations up in MIDAS, and then also combine the combinations into envelopes. For a quick check of what the ultimate strength or maximum service stress was, I also then combined my envelopes into envelopes. I certainly divided that back out to gain an understanding of what the controlling load combination turned out to be, but to get a quick check of what your ultimate moment is or what your maximum service stresses are, it's handy to be able to combine all the envelopes together and just click on one button once the model is run and your performance checks. So that concludes the slide presentation. What I'll do now is pause this for a second and jump into the model. And we'll take a look at how I set this up and go through the bridge. Sorry about that. It seems like I was on mute. Let's start this again. What I'm going through is the grillage analysis and how to set up these girders. And what I'll do is go into the properties of one of the typical sections. And what we do to set this up as a composite section is pick the general composite and then import the section that was designed in AutoCAD into the program to allow for the composite section. Now to set up the section properties, we pick the section that we defined. Software automatically recognizes how many parts it has. And then we pick the stage that we'd like to activate the second part. In this case, I'd like that to happen when the deck hardens. And one thing to remember about the composite for construction stages, anything that we do within this window is going to override anything that's been done before. So it's always a good idea to go through and reset the properties in the construction for composite stage set. And since these will be cured in the casting yard, we'll make them 28 days. That was a brief overview of how to input the composite section. Now I'll turn my groups back on here and have a look at the transverse deck elements. If we take a top view here, this is the Hambly grillage analysis, which allows for these elements to transfer the load transversely between the girders to get the distribution. So when I turn this all on, we can see we have the deck with the section I just described acting in the longitudinal direction, and then the transverse deck elements acting for the distribution. One other thing that's worthy to note here is the other option would be to define the girders only as the girder property and then build plate elements on top to allow for the deck to be modeled as a plate and get the distribution in perhaps a slightly more accurate manner. However, with a concrete structure, we're well within the margin of error to use the transverse grillage analysis. And in addition, the composite element allows the moment and axial force times the moment arm, which is in the deck element, automatically to be transferred to the composite section to allow for more refined and more streamlined analysis and load checking. The next topic I'm going to move into is the time-dependent materials. So for the 9 KSI girder concrete, we have the compressive strength, which, let me turn this back to KSI. So we have the compressive strength, the relative humidity, the notional size. Once that's defined, then we have to link those to the materials that have already been defined. So what I do is pick my material and select which time-dependent material type I'd like for the creep and shrinkage, which one I'd like for the compressive strength. And then add that, and the analysis will take that into effect. The time-dependent material properties are fairly straightforward. We go over to the compressive strength. Just one short note here, this is where I was mentioning earlier that we like to always have at least 3 days of age on the element before we construct it for the most accuracy. If we forget and construct an element at day 0 and do any amount of loading, the behavior is very unpredictable and excessive just because the strength hasn't reached what it needs to from the time-dependent curve. Once we get to 7 or 10 days, it's high enough that becomes fairly accurate. Next topic I'm going to move into is the effective properties that I mentioned. And these come into play in the section stiffness scale factor. I'll point out here that the one that I'll be doing is the pier cap. And to get an appreciation for what that is, we'll turn the substructure on. And the pier cap is this element at the top of the pier at bent 3. Bents 2 and 4 are very similar, slightly different sections, so I'll just focus on bent 3. So when we look at the properties for this, it opens up the General Section Manager window. And just for reference, I'll also show that that can be accessed through the Section Manager and then the stiffness. When we click on pier cap, we can see that I already have what's called in MIDAS the IX value, or typically known as J, the torsional constant. And as I mentioned, we'll reduce that to 1/10 based on the compatibility torsion. So we can type a 0.1 in there, also select what stage I'd like to apply that, with which boundary group, and add it. So that's how to input. It's now a brief explanation of where the compatibility torsion comes into play. We have the bridge in this view. At this pier cap, supposing we had a load on this girder and a load on that girder, which is very likely in a moving load analysis situation, that's going to induce a large value of torsion into the pier cap, particularly at the face of each pier. Now, because this is a straight girder, what we can allow that to do is simply rotate, and that's what that reduction takes into place. We reduce rather than reinforcing for the entire element in its full stiffness, we assume that it will develop some minor cracks while still allowing the structure to remain in static equilibrium. Allow the pier cap to rotate and still stay stable. Now quickly, I'm going to just show some results here. Pause this and pull up the values, assuming that I used a gross section property. And we can see that our torsion over the piers is nearly 5,000 kip feet. Now a quick comparison, if I use the reduced torsional constant, we're down to 1,500 kip feet. And that does exactly what I'm saying. It just allows this section to develop some minor cracking, relieve some of that torsion, and doesn't require us to reinforce for the full value. To put that into reinforcement perspective, that allowed us to go from number 7 stirrups at about 3 inches to follow the ACI torsional provisions to number 5 stirrups at about 9 inches to follow those same provisions for torsion. From seismic demands, the bent cap reinforcement turned into was more heavily reinforced. However, just for the torsion, it was allowed to be reduced. Okay, the next thing I'd like to do here, I'm going to pause this and get my model back. I'd like to just go through all the construction stage analysis, and need to be in the base stage in case we want to make any changes. We'll open this back up and take a look. In each construction stage, we have the stage name, the duration of the stage, which elements we want to activate or deactivate, as well as the boundaries we want to activate, deactivate, and same thing for loads. So as we cast the girders, we're going to build girder 1 through 5. Notice we're not building splice 1 through 5. That will come when we build the splices. The boundaries in this case are what I've called the casting bed. You can take a look at that. And the load will be a self-weight and then some superimposed dead load to accommodate some thickened sections. So pretty straightforward with that. We just go through and make a new load every time we need to change an element, a boundary, or a load case. As I mentioned, I'm going to focus on the boundaries and scroll through all the loadings and explain those as I go. What we'll do is go to the view and turn the boundaries on. Look at the supports, look at the compression and tension spring supports, and also look at elastic links. And what I can do is just turn all of these on and allow anything that I may have in the model to display. Okay, so now in the base stage, we see every boundary condition that I have imposed throughout the model. As we cast the girders, these are point spring supports, and they just allow the girder to camber upward if it needs to, but do not allow it to deflect downward. So it's representing a casting bed. Of course, we'll stress it while it's still in the casting bed. Now we cast splices. This is where we come into the shoring towers. What I can do here is zoom in on one bent. Because of this bent cap and the splice being embedded inside the bent cap, the shoring towers were in one row directly underneath the bent cap to allow for the formwork, but then also a row of towers on either side of the bent cap to support the actual girder, as well as a tower back at the abutment. The solid green boundary conditions, that represents a fixed point. So what we do is we fix that, and I just picked an arbitrary distance down below the girder and then put a compression-only elastic link. And that's where I was explaining before. If when we post tension, any particular one of these would like to lift up, camber upward, it's allowed to. It's not restrained from lifting up. It is restrained from deflecting downward, or in the case of prior to casting splices, falling. Back to the full model. The post-tension stage, we're still on the towers, although we've removed the formwork. So we no longer have formwork at the bent caps, but we do still have the towers. And we've left the towers in place for the deck erection. This is a design decision. You can limit the long-term deflection somewhat by leaving them in place while the deck is poured and cured. Okay, now the deck is cured. One thing I will point out here, just to demonstrate the composite sections and when they can be activated, what I've done is activated everything but this haunched girder at the deck hardened stage. I've saved this haunched girder for the next stage. So if we go to the next stage, we can see then that is fully active. When we go back to this previous stage, it's a good example of what the grillage analysis looks like. So this is my grillage elements. That's distributing load transversely. However, they are weightless and don't allow any dead load. And then once we're up to just aging the structure, this is where the boundary conditions become stable, and this represents the structure in its final state. One thing I will point out is when you have elements passing through other elements, for instance, I didn't need this bent column to start at the top of the bent cap. I wanted to start at the bottom of the bent cap. That's what this rigid link is right here. All that does is physically transfer that node down to this location without allowing any rotation or deflection between the 2 points. It just allows me to build the model in a visually, geometrically accurate way. Okay, next topic I wanted to go into here was the post-tensioning. All I'll do is just turn on Girder 1. So as I said, what we need to do is define the tendon, and then define the tendon layout, and then turn that into a load. So in this case, for the short girders on the end spans, we have 4 prestressing strands, which are internal, they're pre-tensioning. So we select that. The tendon, put in the area, the strand diameter, the other parameters of the strand. For the post-tension tendons, it's a 12-strand tendon. Same thing, we call it post-tension. That allows us to put in the duct diameter, the area, and then also the other parameters, including the friction, wobble, and the anchorage slip when we stress. Okay, so here we have the post-tensioning strand in the first girder segment. Turn on 1 and 2 so we can see how that does not go through the splice. And there we go. We have bottom pre-stressing in the pre-stressing bed that does not transfer through the splice. We do that for all 5 girder segments. And then 2 post-tensioning continuity strands that go from one end to the other. Open up the properties of the strand. So when we put the strand in, model the tendon name, select a group. If we need to put that into a group, I usually just leave them out of the group and just apply them as loads. Tendon properties, pick which elements to assign to, and the type of tendon it would be. In this case, it's a straight girder, so 2D was just fine. And using the spline, I was able to put in the more discrete points and allow it to create the spline between that. Now, because when I established a section property, I built everything from the top of the bridge deck downward. Therefore, I need to put a Z offset downward from the bridge deck to the baseline of where I want the bottom of the lowest point of the tendon to be, and that's where this -51 comes from. As I mentioned, we define the tendon, then we define the pattern, and then we define the load. So I'll open the loads up here. We'll take a look at that. On one of the continuities here. So here we're in girder 1, and it's the second continuity tendon. In this case, I'm stressing from both ends to 0.75. This also gives me the option to stress from the beaning or just the far end. In this case, I will be doing from both. And then what I'll do here while I'm on pre-stressing strand is pause quickly, jump back to this effective model we had. And take a look at the tendon results. So here is the table of tendon losses. And we have a large table of zeros because this is set currently to stage 1 where there are no tendons. What I'll do is turn some of these decimal places down. And also go back to KSI, which is a more meaningful engineering unit. Okay, so we'll take a look at the post-tension losses when we post-tension, and we can pull those values out. And then also go the whole way to 30 years and do the same thing. It creates a real easy table of outputs and allows us to look at that, what the losses are at each step, and see if there are any steps that seem to be bigger contributors than others. The other thing we can do is turn on the tendon loss graph. Same procedure. Start at the post-tension stage all the way to the last step, and then animate that. So we can just take a look at how the losses are through the tendon over its life. And we can do this in either one of the tendons. This is the continuity tendon in the bottom of girder 1. Okay, I'll go back to my model here. And activate all the elements. And what I'll do, I'm going to move on to load. So I'll go through and turn these boundary conditions off so that that's not cluttering the screen. And go back to the base stage. Now, the moving load analysis is similar to the post-tensioning. We pick a code, and we also define traffic line lanes. So here are the 5 line lanes that I've defined. What I've done is taken an assumed offset distance from the barrier rail, and then put the 5 lanes, which do overlap, and will provide a conservative result. For the 3-lane bridge, like I mentioned before, we'll only run 3 lanes ever at one time. I will also define some vehicles. So open this up. Just the wrong one there. Okay, so we have the HL93 tandem, and we'll go through every vehicle, but we also have the 93 truck, and user-defined vehicle, which was the Oregon 2 permit trucks. For the load cases, we have the multiple presence factors. Also combine the effect. Pick the truck, modify this, and this is where we can set the minimum number of lanes and the maximum number of lanes that are loaded, and then also select which lanes will be loaded. The other loads in the model are some superimposed dead loads for the barrier rail, the wearing surface, the standard loads. Also a superimposed load for the haunch. Based on the post-tensioning cambers, we'll have anywhere from a 1-inch to a 3-inch haunch on above the girders to allow for a level deck. And what I did was superimpose an assumed value of 3 inches, which should be a conservative value, and also assume that increase in section depth didn't contribute to the effective composite section property. So that makes it conservative as well, because we assumed slightly thicker haunch, and then also didn't allow that to increase the section property. I won't go through every load I imposed on here. It's pretty standard loads. what I'm going to do now is go into the results and take a look at the load combinations. All my load combinations are concrete design, of course. We have several strength and service loads. So we'll take a look at the strength one. Just has all the parameters of the strength one from AASHTO. Then the same thing with the negative thermal effect. Then what I can come down here and do is create an envelope of all the strength 1 load cases. I have a similar envelope with the strength 2 load cases, and a similar envelope for my extreme events. And then what this allows me to do, and there's one more, so here's the strength envelope. So I combine all my strength cases and created a strength envelope. Then I combine my strength envelope and my earthquake envelope. That's just an example of how I combined the load combinations into the loading envelopes, and then combine the envelopes into a quick check to see what the ultimate load shears and moments were at any given element. Now once I had those values, it was necessary to go back through and do a little bit more refined analysis to determine which one was controlling. Okay, and the final thing I'll go through here is just a few results. Get my model back. So here we're at bent cap 3, and this is the effective properties, so we have the reduced values for the torsional moment. What I'll change that over to is the bending moment. And if we put the diagram on, it makes it a little bit easier to see what's going on. Usually with the diagram, we don't need the values with the legend. And of course here, we can use these load combinations that I've set up. Take a look at strength 1, and so on. Looks like I have a few more minutes. I'll just jump into the extreme event and just look at setting up a response function and response load cases. Like I said, we didn't spend a lot of time analyzing any of this. We simply used the design loads for the area and set up a response spectrum and a response spectrum load case. So this is the response spectrum, and that's set up by typing in the response, the design spectrum, which came from the Oregon Department of Transportation. Did that and got the spectrum. And then we set up the load case by using the function name, the load case name, with a scale factor, and we left our scale factors and period factors at 1, and have a longitudinal and a transverse case. Okay, so I'll go back to results and have a look here at a comparison of that earthquake load to the strength load at the pier cap. Turn our values back on. And we can see that the moments of those pier caps from the seismic event were significantly greater than just from the strength case.